Dear participants, in another 5 minutes, we'll be starting with the section. We are waiting for the guest to join. Once he is joining, we will start the section. Thank you for the understanding. Uh, Amit, sir, sir, are you able to hear us, sir?
Now you're able to hear me?
Yes, sir. We are able to hear you, sir. Uh,
Okay.
uh, can you verify whether the
Is it
presentation?
audible?
Yes, sir.
Yeah,
You're
yeah.
audible, sir.
Yes. I'm able to hear you people very well. Yes.
Sir, you may try to share something, sir, so that we can verify it whether is there any technical issues or something, please.
Okay. Let me see. if you're able to see this one. I've shared my presentation, but let me know if you're able to see it. Yes. Okay.
Yes, sir. It is visible now, sir.
It's
Okay,
visible,
thank
sir.
you. Okay, thank you. So I
So
can,
shall I? Can I go with the official start, sir?
yeah, sure. Thank you very much. Okay.
Okay, sir. Thank you very much, sir. Very good evening to one and all present here in this virtual gathering. We, Dr. Mahalingam College of Engineering Technology, welcome you all for the ATAL FTP, 60 ATAL FTP. Now, I would like to uh, give a short note about our today's guest. Our today's guest is Dr. Amitkumar, is an assistant professor at the Department of Electrical and Electronics Engineering at the University of Cagliari, Italy. He earned his master's degree in physics with a specialization in photonics from the Satya Sai Institute of Higher Learning in the year 2004, followed by a doctoral degree in physics through a prestigious Marie Curie fellowship at the University of Cagliari into the year 2009. Dr. Kumar's research focuses on innovative areas such as computer simulations, renewable energy, power electronics, wide bandgap device, and battery energy storage systems, highlighting his commitment to advanced technology in storage systems in sustainable energy. In addition to his research, he actively contributes as a guest editor and reviewer for various international journals, fostering academic excellence and collaboration. His career has included significant roles such as participating in enormous staff mobility for teaching at the Center of Electronics SDU in Denmark. He has also served as a visiting researcher at IIT Roorkee and held a visiting scientist position at the Center of Advanced Studies, Research and Development in Sardinia from 2011 to 2014. Dr. Kumar is dedicated member of IEEE and IES Technical Committee on Power Electronics, reflecting his engagement with key professional communities. He has made substantial contribution to several projects, including two funded by European Union, and has authored over 70 papers published in international peer-reviewed journals and conference proceedings. His role as an editorial board member of the Pillows One journal since 2023 further illustrates his commitment to advance scholarly communication and research integrity. Now, I request Dr. Amit Kumar to go ahead with this lecture. Sir, please.
Okay. Yes. Thanks a lot, Dr. Malingam, sir, for a very nice introduction. I thank your college and through the ATAL FDP program of giving me an opportunity to share my a little bit about my research, which I perform at University of Cagliari. So, good evening to one and all. So, the title of today's seminar or the talk would be Performance Benefits of Wide Bandgap Devices in Electrical Vehicle. So, my okay. So the outline of today's talk would be as follows. So in the first part, I will give a brief introduction to electrical vehicles and followed by wide bandgap devices. Then we will look into some details about the fundamentals of wide bandgap materials and how are they useful in the field of electrical vehicles. And then we will try to see about the performance benefits of using this wide bandgap materials in electric vehicles. Then I would try to present to you a case study and some real world applications where we are able to see the application of wide bandgap materials into the electrical vehicles. And finally, I will conclude with some future trends and some opportunities which hold for us in the near future. So now looking into the first slide where it is concerning overview of electrical vehicles. So electrical vehicles have a history that dates back to the 19th centuries with early prototypes that have emerged in the 1820s and 1830s. However, what we know is that the internal combustion engine, which dominated the automotive industry for the most of the 20th century, was basically due to its superior range and energy density. But what we can say is that the modern resurgence of electrical vehicles began in the late 20th and the early 21st century, driven by the concern, in particular, over the environmental pollution, the climate change, and also thanks to the advancements in the battery technology. So, what we know is that we have, for example, the revival of the electrical vehicle was due to the California Air Resource Board, which pushed towards zero emission vehicle, leading to the development of models like General Motors EV1. What we see in the 21st century boom is that we have vehicles like Tesla road coaster, which was in 2008, that has revolutionized the electrical vehicles mainstream where the adoption has begun. What we can also say is that since EV has gained a significant traction and major automakers apart from Tesla, like Nissan, Chevrolet, BMW, and Volkswagen are also entering the market in partly proposing hybrid electric vehicles, and in some cases also completely electric vehicles, fully electric. Moving on to the next slide, where I show to you what is the current trend for the electrical vehicle that we see here. So what one could say is that the global EV sales have surged with over 10 millions of electric vehicles which were sold in 2022, representing an increase of 55% with respect to that of 2021. I apologize that I don't have the data for 2023 and 2024, so that's the reason I'm presenting you the data of 2022. But what I can say to you that the trend is always on the increase also in the last 2 years. Another important thing is that the use of electrical vehicle has received substantial government support, especially in European and developed countries, where the governments are offering incentives and also provide tax breaks to promote people to adopt to the electrical vehicle. One of the example is like we can say in Norway and also even in Italy, where the government is promoting people to move to electrical vehicles with the target being 2030, where the production of the standard vehicles with either diesel and petrol are planned to be stopped. Another important part is regarding the technology advancements. As we can see that now we have lithium ion batteries which are able to provide a wide range of tension and also have reduced, we also have a reduced cost for them. Okay, so this is also one of the reasons why we are seeing an important surge in the electrical vehicles. And finally, what we can see is that we are having a major investment, particularly if the electrical vehicle have to compete with the normal vehicles. You need to have charging infrastructures. So what we know is in that most of the developed countries, and also what I got to know also of some developing countries, you have huge investment both from the public and the private enterprises in building setups or building places so that to facilitate the charging of the electrical vehicles to so as to spread the application of electrical vehicles in an aim to eventually replace them with the standard vehicles. So moving on to the next slide, what are basically the key challenges what we have in this electrical vehicle design? Okay, so one of the key challenge is regarding the efficiency. So when I talk about efficiency here, what I mean is energy consumption and the thermal management. So electrical vehicles must optimize the energy used to maximize the range and reduce the load on the power grid. Otherwise, if if all the energy we take always from the power grid, this is would not be the optimal situation. Second part which concerning efficiency is also the thermal management. So we need to have efficient cooling and heating systems that are critical to maintain the battery performance and also its longevity. And the second challenge is the range. So what we can say is that the capacity of the batteries range have improved. Okay. However, many electrical vehicles still fall short of the range that are offered by ICE vehicles, especially for the long distance travel. Talking about the range, the next part is also concerning the energy density. So increasing the energy density of the batteries without compromising on the safety and the cost also represents a key challenge. The third part is regarding the charging time. If electrical vehicles have to compete with the conventional vehicles, one needs to reduce the charging time, or it should be at least in a time frame comparable with the fuel filling capacity of the standard vehicles. So what we know or the technology is always pushing towards fast charging technologies that can charge electrical vehicles to 80% in, in a time range of 20 to 30 minutes. But this is still slower than refueling a conventional vehicle. Another part regarding the charging time is also with respect to the infrastructure. So the availability of fast charging stations is still limited. And what we know is it is particularly present only in the limited in the rural areas. Whereas if you go to the urban areas, there you have the infrastructures. So if we want the adaptation of electrical vehicles, one needs to make huge investments in the infrastructure also of the for the charging of the electrical vehicles. Finally, but least but not the it's also one of the most important aspect is regarding the cost. So when we talk about electrical vehicles, uh, one of the most expensive component of an electrical vehicles are the battery, which basically account for the significant portion of the total cost. What we can say is that the prices have dropped. However, further reductions are still needed to make electrical vehicles more affordable. And another challenge together is that what do we do once the life time of the batteries in the electrical vehicles are over? So there is another challenge, okay, regarding environmental or how this batteries which are used in electrical vehicle can be recycled for, let's say, any other applications, so that we have also the part of sustainability, which is also one of the major concerns when we speak about batteries. Another way to bring down the cost is by scaling up the production to meet the growing demand while maintaining still the quality, and reducing the cost is still, or it still remains a challenge for the automakers. So in summary, what we could say is that addressing these challenges still requires continued innovation in the battery technology, in the material science, where we have to look for new materials, and also infrastructure development, together with the support of policies uh, from the government. And another important aspect is the education to the consumer about the electrical vehicles. Moving on next to my next slide, it is now regarding wide band gap devices. As in the previous slide, I was mentioning that the challenges is that we need to look for new materials which are able to give us the maximum efficiency, especially in the scenario of wide electrical vehicles. So here I've shown you a very simple representation to let you know what do I mean by wide band gap materials. So generally, what you have is you have two bands. So one is the valence band and one is the conduction band. So just to this is a basic chemistry things which you must have seen also in your high school, or even in the, let's say, in the first few years of your university courses. So the gap between the valence and the conduction band is referred to as energy band gap. So what we can say is that wide band gap materials have a band gap which is larger than the traditional silicon. Uh, so just to give you a number, silicon have a band gap of 1.1 electron volt. Okay, so electron volt is basically the unit of measurement, in this case used for measuring the band gap. While what we can say is that some of the wide bandgap devices like silicon carbide or gallium nitride, which we will be discussing them in the next slides, okay, they have a band gap which is close to 2.5 times that of the band gap of silicon, standard silicon. Okay, so just to give you a number, silicon carbide has a band gap of 3.3, whereas gallium nitride has a band gap of, let's say, 3.5, 3.6. Now, what I will not be discussing much about the another materials which are also called as ultra wide band gap materials. So one of the example is diamond. Okay, so diamond in this case has a band gap of, let's say, 5 electron volts. Okay, so we will see that having a higher is the band gap, one has, let's say, high voltage tolerance. Okay, so the device which is made with wide bandgap materials is able to withstand high voltages, is able to show or display high thermal conductivity, and also fast switching speeds. Okay, especially when we talk about electrical vehicles, we are talking about charging um, the batteries. Okay, so in this scenario, what we will see is that with respect to the traditional silicon based devices, wide band gap materials have always a superior characteristic. Moving on to this slide, which is which I basically would like to draw your attention, because if you look at the periodic table, okay, so it is now due to the let's say the boom or of artificial intelligence, no, even in with the aim to find the right material for the right application. So here what I've shown to you is that from the periodic table we have group 3 and group 5. Okay, here I have shown some of the semiconductor materials through from which we have the possibility to find the right materials which can be used for electrical vehicle application. Now, when I say right material, it means a combination of one or two of them together with a doping concentration which can vary in the applications which one needs to achieve. Okay, so I will not be getting into this details of how you prepare this material, but what I would like to draw your attention is that what I've shown you in this slide here is that let me show with the pointer. Yes, so here what you're able to see is the same part. What I was showing you is the valence band and the conduction band. As you can see, this is the traditional for silicon, whereas if you go for silicon carbide and GaN, you are able to see that the band gap is much longer. And even if you go way all to ultra wide band gap material, which I was telling you regarding diamond, one can see that it has a huge band gap, even higher with respect to the wide band gap materials like silicon carbide and gallium nitride. Moving to the next slide, where I try to explain to you some of the properties which are important for or which make silicon carbide one of the most mature semiconductor present today. So what is the important aspect is that silicon carbide, it is basically an indirect band gap material, and we see already its application in different applications of power electronics. Okay, so what we know is that the first major supplier of silicon carbide wafers was basically founded in 1987. Okay, so the first type of silicon devices were the Schottky diodes, which had a maximum operation voltage of 600 volt, which is basically twice that of 300 volts, which can be achieved with silicon. So as you can see, moving or combining silicon with carbon, which when you get basically silicon carbide, and then you can have different doping concentration of silicon with carbon, and then you are able to achieve twice the operation voltage in which you would achieve with that of silicon. Another important part aspect which I would like to highlight is that silicon carbide diodes are commercially available. Okay, and whenever we use any power device, we say what are the ratings. When I say rating, it means what is the current and what is the voltage. So what we can see is that silicon carbides are available at a rating of 20 amperes at 600 volts or 10 amperes at 1200 volts. Okay, so this are some of the key aspects of silicon carbide. Moving on to that of another wide band gap material, which is now being the hot topic, especially in power electronics, is gallium nitride, or also abbreviated as GaN. Okay, with respect to that of silicon carbide, GaN is a direct band gap material, and we see its application in power electronics and also in optoelectronics. Now, with respect to that of silicon carbide, what we know is that the switching performance of GaN is much better than that of silicon silicon carbide. Okay. Another part which we know is that the GaN diodes have lower switching loss and which is independent of temperature. What does it mean? It means we can use this material for high temperature applications. Okay. And another key aspect is that due to its wider band gap, okay, the GaN diodes have higher working voltage than that of silicon carbide. But what still remains a challenge is that how you crystallize this kind of materials for the application. One is that you say, okay, this material shows such wonderful properties, but if I need to crystallize it or to make this material, what are the challenges? Okay, and what is the cost? What is the security? So there are different challenges one needs to also take into consideration when choosing the right material, especially in the landscape of electrical vehicles. Moving on to the next slide, what you can see here is that I have provided a sort of a comparison. I have just chosen 5 parameters, which to give you an quick overview or to just be able to convince you that wide bandgap devices have better application, especially for the electrical vehicle scenario. So what you can see here is that we have band gap of 1.1 electron volt, which I was telling you previously for silicon, whereas we can see for the wide band gap, in this case, what I am saying is silicon carbide and gallium have 2.5 times the higher is the band gap. Second part we can say is when we talk about the efficiency, we can say that the efficiency of the wide band gap devices are higher at high temperatures. Okay. Another important part is the switching speed. Okay. So also in this case, we see that with the wide band gap devices, you can achieve a switching speed, okay, which are much faster than that of comparable to that of silicon based. Just to give you an example, sometimes you have a switching speed of wide bandgap materials to be in the order of nanoseconds, whereas when you talk about silicon, we are in the order of, let's say, microseconds. Okay, so the fourth aspect is concerning the thermal performance. So also here, what we can say is that the wide bandgap devices demonstrate a superior thermal performance whereas the silicon have a moderate performance. The another and the final crucial aspect is the size and the weight. So why are we all now thinking to move to wide bandgap devices? It is because using wide bandgap materials to make the power electronic devices allows us to pack large amount of power in a smaller space. Okay, so you have devices which are smaller in size and also which are lighter, whereas when we talk about silicon, they are larger and also heavy with respect to the wide bandgap devices. But one of the challenge which still remains in the adaptation of wide bandgap devices is the cost. Okay, because silicon based devices are much cheaper than the ones of silicon carbide or gallium nitride. Okay, so this cost actually is one of the main bottleneck, and the adaptation of this new technology for different applications, in particular also for the electrical vehicles. Now, in the next slide, what I do is just summarize to you the the key four aspects of why one should go to wide bandgap devices. Okay, so here what you can see is that I have shown to you that wide bandgap devices, they offer high efficiency, they are more reliable, they are faster, and they have a smaller size. Okay, but always I would still like to pay emphasis on the part of the cost, which still remains a challenge for us. Okay. Moving on to the next slide, where I show to you a landscape of the operating frequency and the system power level. Okay, so here this is a landscape where one could look how does silicon devices stand with respect to the wide bandgap devices. So what one could see is that when you have lower operating frequency, let's say between 10 hertz to even thousands of hertz, even if to 100 kilohertz, you still have the silicon MOSFETs, which have the operating frequency, let's say generally IGBTs have in the order of 20 kilohertz, whereas you have some silicon MOSFETs can also reach up to the operating frequency of 100 kilohertz, but they have the system power level is what they can reach is up to 100 kilowatt. Okay, but now if you look at the wide bandgap material, in particular is silicon MOSFETs, okay, they are able to arrive to the voltage even up to 1700 volt. Okay, whereas if you look on the on the other hand, if you look at gallium nitride transistor, we are able to achieve the higher operating frequency. Okay, even something around 5 megahertz, but what we are still limited due to the technology here is that we are not able to achieve the higher power level which we are able to achieve either with silicon or with silicon carbide. So that is one of the reasons why, especially when we talk about electrical vehicles, and in the other slides, I will try to make it more clear where you have different applications. So where you have low power application, there we see the usefulness of gallium nitride. Whereas where you need higher voltage applications or the need, in that scenario, we have silicon carbide. Okay, now moving on to the next slide. Here, I have shown you based on the technology need, what are the features, and what can be the different applications. Okay, what one can use for. Uh, so, for example, if one looks here, we have silicon for high voltage MOSFET. So they have basically the feature where we can use them for medium to high power, high voltage, several kilowatt, and also let's say we can arrive up to a high frequency, but lesser than 20 kilohertz. What are they ideal for, especially when we talk about also in scenario of electrical vehicles? Okay, generally they can be used for lower power motor control, on-board chargers, and also can be used in the charging stations. When we talk about always IGBT, it means always silicon based. Okay, they can offer really high power, high voltage, and they also have a medium frequency where one could achieve up to 50 kilohertz. Okay, so generally here when we talk about IGBTs, what we see is that they have their application in HV motor control, in UPS, induction heating, and also, especially when you talk about electrical vehicles, in the main traction part. Next, moving on to silicon MOSFETs. Okay, in this in this part, they are able to not only achieve high power, high frequency, and also have they are able to operate at high temperatures. So these three features really make them ideal for high power DC-DC charging station, okay, and also for the main traction inverter. Moving on to GaN transistors, what we saw already in the previous slide, one is able to achieve very high frequency, that is, you're able to go close to almost greater than 80 kilohertz, in the order of even megahertz in some cases, and they are able to be useful for medium high power, usually several kilowatts. So generally where they have most application is that you are able to find them in SPM, SMPS, in the telecom power, okay, or in the PV inverters, or also in the LiDAR applications. Moving to the next slide, I try to show to you how can one say that GaN is useful for the electrical vehicles. Okay, so already I think by now you must be already aware that GaN is a wide bandgap semiconductor. What is the impact, okay, of using GaN in electrical vehicle? The first part, it reduces the system weight, and the second thing, it enhances the performance and extends the EV range. Okay, this is one of the most important part which one needs to consider. Now, once when we talk about key application of GaN in electrical vehicles, so here what you see is that you are able to see that you have onboard chargers. Okay, so in the case of onboard chargers, what you have is that they have been used actively for higher efficiency and power density, and then you are also able to reduce the size and the charging time. Moving on to the part of the DC-DC converters, what you can say that in this case you have low energy loss and compact designs, and then what you know is that you also have high performance solution. And the last part is regarding the powertrain integration. This allows us to eliminate redundant hardware, okay, because when we move to higher switching frequencies, okay, the passive components which we use in our power electronics, like the inductors and the capacitors, we are able to reduce the size of these passive components, okay, thanks to the higher switching frequency. Okay, so this allows us to reduce the redundant hardware, and as a result allows us also to reduce the weight and improve the efficiency. Okay, so I think what one can say is that wide bandgap semiconductors, okay, not only allows us to reduce the weight and size that are an important aspect to be considered in electrical vehicles, especially in comparison with the conventional internal combustion engine vehicles. Okay, another part which we saw is that silicon carbide and gallium nitride are able to switch at higher frequencies compared to that of silicon power devices. Okay, this not only enables us to have smaller and lighter power converters, but also better electromagnetic interference, which is also a very crucial aspect which we need to consider when we are comparing the wide bandgap technologies with the silicon design. Okay, so these attributes together contribute to the improvement in the range of the electrical vehicle and also allows us to reduce the range anxiety of electrical vehicle users, because the main challenge or is that till what is the range through which I can drive my vehicle and I don't have to worry that my charge of my battery will be finished. This is one of the main anxiety of especially the electrical vehicle users. So incorporation of these technologies, okay, especially the use of silicon carbide and gallium nitride, helps us to achieve the higher voltage applications, okay, like the traction drive inverters uh, in the conventional electrical vehicles. And then what we know is that there is the bidirectional DC-DC converters where the power levels can range from 60 to 150 kilowatts. Moving on to the next slide, where I showed to you the landscape here, where I've shown to you is the power and the frequency with not only with the applications, but also here to show to you which applications inside the electrical vehicles, okay, what kind of frequency is required and what levels of power is needed. Okay, so in this figure, what you are seeing here, what we can say is in this figure, we can say that silicon carbide competes with the silicon in the high range of power. Okay, where you have basically the high range of power here. You are seeing that's sorry, I just use a pointer. It's better. Okay, so you see for the high range of power, you are seeing that silicon carbide is competing with the silicon application, which is shown in the gray, whereas silicon carbide is shown in the orange, and you're seeing for the GaN are shown in pinkish color. Okay, so whereas what you can say is that you have that the GaN competes in the lower range of power. Okay, so you can see in the lower range of power you are having the completion of this. Another part, what you can see is that especially if you look now here at the different applications that you have here. So here also is the same, where within the switching frequency, where you have for the traction inverter, the boost converters, the different when you have in the electrical vehicle, you have the onboard chargers, you have the DC-DC converters. So you can see that where you have high frequency applications, we have the superiority of gallium nitride. Okay, now moving on to the hybrid electrical vehicle ecosystem. Okay, so here what I've shown to you is in this slide, in this picture, what you're able to see is the hybrid electrical vehicle ecosystem. Okay, what you see here is that here to have an ideal hybrid electric vehicle ecosystem, we need to realize the right place where we can use silicon carbide and gallium nitride, no, which I was telling to you. For example, here you have traction inverter. So in this case, some where you can go for silicon carbide. Okay, then you have power DC-DC converter. So you can see here that the hybrid ecosystem of an electrical vehicle is consist of a motor, followed by a traction inverter. Then you have power DC-DC converter. Okay, then you have a battery. Then here you have this onboard chargers. Okay, for in this case, one could try to use also gallium nitride. Then to have this fast DC charging, and then other aspect, what you have is also the fast AC charging. Okay. So what we know is that with this rapid development of electrical mobility, we have that more and more newly battery developed electrical vehicles are being produced. Okay, so for sure, here what I've shown to you is sort of a hybrid EV ecosystem. Okay, here it is not completely, is not fully electric. Okay, so now moving to the next slide. Here, what I've shown to you in detail, especially if the audience is from electrical background or even electronics, you can see here when I talk about the traction inverter or the high voltage DC-DC converter or the onboard chargers, you can see that here we have different, in this case, you have MOSFETs, okay, and then you also have passive elements like the inductor, then you have different electronic components, okay. So you can see that using, when I talk about wide bandgap technologies, what I mean is to replace this, here what you're seeing, the MOSFETs, no, maybe with wide bandgap like silicon carbide MOSFETs, or also with gallium, it's called as GaN HEMT, which is high electron mobility transistors. Okay, so when I say the importance of wide bandgap material is basically, if you look at the different topologies which we have for the traction inverter, for the DC-DC converter, and on the onboard chargers, here we have the need to replace these aspects. Okay. Okay, moving to the comparison, okay, of GaN versus SiC in electrical vehicles. What one could say is that in the case of GaN, which I was telling to you also before, we have the applications in the mid power range. Okay, that means you can go up to from, let's say, 48 volts up to 400 volt systems. Okay, whereas when you have for silicon carbide, you have higher power. Okay, so basically when you have the charging stations, they are basically adapted with silicon carbide technologies. Okay, so you have something like 800 volt system. Okay, now here what I've done is I have done a comparison, okay, between the two wide bandgap materials. Okay, so that's the reason why you see the switching speed of GaN is high. Okay, it's basically over 100 volts every nanosecond. Okay, so in this case of, if you look at silicon carbide, it is moderate with respect to gallium nitride. Okay, another part is the adoption of this GaN and the SiC technology. Okay, so what you have, you can also have a GaN on a silicon. Okay, so in this case, you are trying to bridge two kind of materials to maximize, you know, the efficiency, minimize the cost. Okay, and there are also some things related with how you make the materials. Okay, so whereas you see that silicon carbide, it generally dominates itself in the traction inverters. Now, one of the challenges which one sees, okay, especially in one of the challenges is the also, especially regarding the design of this kind of material, is also regarding the wafer bowing and defects, especially when we make the gallium nitride wafers onto the silicon chip. Okay, so these are some of the aspects which one needs to take care, especially when you are and when one is designing this kind of materials. Okay, another point which I forgot to mention before, that is like when we look between GaN and silicon, they have more or less the same thermal conductivity. Okay, while what we know is that silicon carbide is over twice as good, okay, in conducting heat, even better than silicon and also gallium nitride. So we have some cases where, you know, GaN is having some characteristics which is lesser than that of silicon carbide. So the main aim is to see where each of this material find their applications. Okay, so for this reason, because silicon carbide has a relatively low thermal coefficient of expansion, it makes them less prone to damage from high temperatures. Okay, so in many applications like the onboard charger, okay, in this case, the choice between GaN and silicon carbide is still not always a clear cut. Okay, so what is now the shifting designs basically of the onboard chargers, okay, which are basically one of the most crucial part when we talk about the electrical vehicle designs. So what we are seeing is that there are basically two classes of the onboard chargers, which have the range from 7.2 to 11 kilowatt single phase and 22 kilowatt three phase. Okay, so one of the main challenges in designing onboard chargers is that the electrical vehicle battery pack voltages are continuously rising. Okay, so just to give you an example, with a 400-volt battery pack voltage, in this case, GaN is often selected for onboard chargers. Okay, whereas if you have 800-volt electrical vehicle battery packs, in this case, you have silicon carbides are preferred. So based on the battery pack voltage which you have in your electrical vehicle, you either prefer gallium nitride or you prefer silicon carbide. Okay, so what maybe in the next slide we will also see the other crucial aspects. So another part which I was talking before, maybe if I show the previous slide, it becomes much better. So here, if you look, this is this power DC-DC converter. Now, also in this case, what we are seeing is that in this case, you have 48-volt DC mild hybrid electrical vehicle. In this case, is you are seeing the use of gallium nitride. Okay, one of the reason which makes gallium nitride right solution is that it enables the power converters to switch at 250 kilohertz compared to that of 125 kilohertz where we use traditional silicon MOSFETs. Okay, so as you can see here, which I was telling you about the power converters here, you are able to see that using gallium nitride, we are able to switch at higher frequencies. Okay, now switching at higher frequency not only offers us an increased efficiency, it makes the size of the converter smaller rather than using if you use silicon carbide. Okay, and another part is that it also allows us to have a lower cost because we're using lesser components, we have lesser cost. with respect to when we go for the silicon-based applications. Okay, so based on what we use inside, one needs to find the utility of the wide bandgap materials. Okay, so moving to this powertrain system, in this case, what we find is that GaN is much suitable in this case because one of the key features is that it has a higher switching frequency. Okay, zero reverse recovery. This is one of the characteristic which is very much particular for GaN. And the benefits of this are especially, okay, here you can use them for different configurations. Okay, so you can use them for LLC, resonant DC-DC converters, which I showed you in the electrical vehicle subsystems. And then the benefits of these are that you are able to reduce the system weight and improve the efficiency. Okay, so they also enable us to have a sort of compact and high performance design. Okay, moving to the last part, which is regarding a small case study. Okay, so here I just show you a very recent application or recent news, okay, where an Chang'an Automobile, okay, they proposed a breakthrough in electrical vehicle charging technology. So these are some of the technical part which you can see here, which I've shown you. So what they have introduced is the first commercial gallium nitride based onboard charger, okay, which we were speaking here. And they were able to successfully integrate this into the electric SUV pickup hybrid. Okay, so here are just the specific specifications, okay, of the single motor. So you have 343 horsepower, which is equivalent to 252 kilowatt. Then you have the dual motor, okay, and what is the top speed is it can achieve is 210 kilometers per hour, okay. And here the batteries which are used are basically the ternary lithium batteries, okay. So what we know is that they have built, this is an original electric SUV pickup hybrid, okay, and then we can see the other details. From the innovation, it is they were able to integrate the GaN technology, which is something new, okay, and they have been collaborating with Navitas Semiconductor Technologies, okay, which is a company which produces this GaN devices, okay. So what we see is that if one has to achieve a breakthrough in EV charging technology, because we want to compete with the conventional ICE vehicles. Okay, so in this case, we need to see how one could reduce the charging time of the electrical vehicles to be comparable to that of the conventional vehicle. So in this case, it is very important to look at the innovation and also the partnership with different industry partners. Okay, so what are the key benefits which the automobile Chang'an was able to achieve when they adapted gallium nitride? Okay, what they said is that it allowed them to have an increased power density. So it was more. Sorry, I'm sorry. Okay. The, the, there is some disturbance, I think. Okay. Thank
Yes,
you.
sir, it is rectified. It is rectified, sir.
Okay.
Go ahead,
Thank
sir.
you. Thank you. Sorry. Okay. So So one is you have the increased power density, and then you are able to have also higher efficiency. Okay, what they say is that they were able to achieve an efficiency of 96% in charging and discharging, and they have a power density of 6 kilowatt per liter. Okay, so they also say that using this gallium nitride, they were they might be able to prolong the lifetime driving range of this car by about 10,000 kilometers. Okay, so uh, one of the challenges which the company also mentioned is the possible cost reduction. Okay, so they hope that in the near future they are able to reduce the cost by 15 to 20 percent decrease in this part. Okay, so here, I mean, this is, I think this was launched in October 2024. So I would say this is relatively new regarding this part. Okay. Moving to this part here, which I was telling to you that, so basically this company, they used this GaN safe power IC chip, okay, from this company Navitas, okay, which allowed, you had this efficiency increase, you had the benefits. So this tells us or shows us a real case example where when using this kind of wide band gap materials into the electrical vehicle ecosystem, you are able to reduce the charging cost, you are able to increase the efficiency. Okay, so these things are really very encouraging when one moves towards adoption of wide band gap material into the electrical vehicle technology. Okay, another part which we can say is that this GaN technology has allowed to have smaller, lighter, and high efficiency design. Okay, so this is also one of the most important part which one could needs to mention, and especially when we talked about the EV charging and adoption. So using this GaN based for the OBCs, okay, you are able to have the high voltage architectures up to 1250 volts. And then another part is that you have an efficient charging, okay, which also relies, okay, when you talk about the electrical vehicle, you have the efficient charging is relies on the onboard charger. Okay, what does this onboard charger do? Basically, it converts the AC power to high voltage DC for the battery storage. Okay, so when you have, let's say, a 800-volt battery system, you go towards, let's say, which would require 1200 volts, you use silicon device. Okay, but what we can say is that GaN is also suitable for onboard charger systems up to 650 volts. So what we know is that companies like Navitas, they are advancing the GaN-based OBC technology with monolithically integrated drive, which have control features that allow them to improve efficiency and um, reduce the component cost. Okay, so finally, I conclude my final slide. Okay, so here are just small takeaways from my presentation. Is that wide band gap materials are a key play a key role in developing new technologies in EV. They enable smaller, lighter power converters and are able to achieve higher conversion efficiency to improve the range of electrical vehicles. Okay, while there are places where we see silicon carbide and gallium nitride compete with each other, okay, but there are also a clear use case for both of the technologies. No, like I was saying, when you have higher voltage, you go for silicon carbide. Where you have mid voltage range, you go for gallium nitride. Okay, so in conclusion, what I could say is that, even though the acceptance of electrical vehicle is now becoming fast, okay, what still is remains a challenge is the expansion of the infrastructure for charging. Okay, what does the scientific research indicate that this charge anxiety, still they have the people, oh, okay, my vehicle is going to go run out of charge, how much time do I need to again charge back, uh, this charge anxiety and not the range in restriction that reduces the consumer confidence. Okay, so generally what we would say is that electrical vehicles must have at least 350-mile ranges with 20-minute charge time. Okay, so and then this is basically the time let's say as of now people are moving towards. Hence this would not only allow to reduce the stress and need of going for further fast charging, but they also would pay a way for improvement in both onboard charging and also for the roadside charging technology. Okay, so when you talk about roadside charging technology, there you use silicon carbide. When you talk about onboard charging technology, you talk about gallium nitride. Okay, so you see that there are both of them in perfect perfect, I would say, synergy between them to build an efficient, ecosystem. Okay, so thanks for your patience. I hope I was able to give you an overview of the performance benefits of wide bandgap material in the electrical vehicle ecosystem. If there are questions, curiosity, I'll be happy to answer. Thank you.
Thank you so much, sir. Thank you so much.
Thank you.
Given a revised spread of knowledge, sir. Participant, if you have any queries, you may post the same in the chat box. If you have any queries, you can post the same in the chat box.
Or I can always give my, eventually if they have curiosities, I will be happy to, even respond through you if anyone is interested in something. So it's not a problem. Okay.
How to reduce the charging time?
Okay. No.
Question.
Okay. Yeah. Okay. So as I was telling to you, I mean, charging time. What one could, when we talk about charging thing, it's like how much charge. One already when we moved from the silicon devices to gallium nitride, we have been able to reduce this charging time. Okay, so one of the thing would be to find still the right material, or already the material which we have, let's say gallium nitride with the appropriate doping of some impurities which allows us to do it. Okay, but I think as of now what we are able to achieve is 20 minutes of charging time, which is relatively, I think it's still not competitive with respect to that of the conventional ICE, but I think it is still a significant improvement with respect to the silicon. Okay, The second question I think is, I think it's more or less related to the same, the increasing the electrical vehicle range. When you say increasing electric vehicle range, we always think of the batteries, no? For example, so based on the different batteries, you can have 800 volts, you can have 400 volts, so generally, I think the new electric cars which are coming up, they guarantee, let's say, up to 250 kilometers, with a particular speed, let's say 100 kilometers per hour. Yeah, you don't have to worry. But what is generally a good practice is that to never let the charge of your vehicle drop less. I mean, if it at least 20% charge, if it is left, you should do the charging. You should not let your charging to come to zero and then think of charging your vehicle. So that's one of the practice which is very, very important. Okay. Yeah. Thank you. I am happy that this talk was very informative. Thanks a lot. Okay.
Thank you very much, sir. Thank you very much for your being with us and joining with us in this 60 ATAL
Yeah.
FTP. Thank you for
Okay.
being with us.
I'm very sorry for the initial delay because I counted it wrong, because I forgot that we are 4.5 hours behind you. So, but anyway, thanks a lot. Sorry again
No
for
problem.
my
No problem, sir.
delay
No,
in joining and the
no,
thing. Okay,
no
apologies
problem, sir.
because
No problem, sir.
I see how difficult it is to organize this. I really thank you for a wonderful organization and thanks for your kindness too. Okay, good. Thank you.
Okay, sir. Thank
So,
you very much.
okay, thank you. Okay, bye bye. Thank you.
Bye. Bye, sir. Bye, sir.
Bye.
Participants, your feedback link is available in the chat box. You may fill the same. And the next section will be started sharp by 7:30. 7:30 sharp will be starting the next section. So I request all the participants to fill the feedback form. It is available in the chat box. You may stay in the same link for the next section too.